Good again. As we proceed with the water engineering, remember the current chapter now we're dealing with the stormwater. Now on the stormwater itself, there are possible calculations. Say you are provided that you are provided with settlements. Let's say there are about 2 settlements. Now in these settlements, you are told that you are set to calculate, to design a pipe going from that end to that end. That's the use of pipe 1, right? And then you also design a pipe going from that end to that end and joining the possible river. Now, if your system of analysis is in this format, then you notice that maybe you are provided an area there and you are provided a C value and probably you are provided a time of flow. The time of flow in this context is in minutes, and then the C value as well as your area. You must take note of the area that is provided in hectares, and you must understand when is that going to change. And then the area of this side, let's say this is A and that is B. The area of catchment B will be sitting at about 0.013 square kilometers. And then you've got a C, which is about 0.15. And then you've got your time of flow, which is sitting at about 6 minutes. Now yours is to say you've got manhole 1, manhole 2, and the river. So that is your pipe 1 and that is your pipe 2. So that is the expected design for you is to actually size the pipe 1 and size the pipe 2 and provide the outflow that comes out of pipe 2 into the river. That is what the actual design office is looking for you to develop. Now, in terms of going about the calculation of this, one is expected to have completed a table analysis, because this is actually quite better explained in a table format. Now, one would want you to provide the line. What is the line that you are dealing with? The line that I'm dealing with is manhole 1, 2, manhole 2. That's the first identification. And then the area, which is important. Now the area here is area A, which contributes to manhole 1, and then area B, which contributes to manhole 2. So area A, it's 1.2. Remember the area is in hectares according to the table. 1.2. And then your last line here, your area is 1.3. Manhole 2 to the river. And then your C value, your coefficient of runoff, becomes 0.2. You simply take it from there, and then you bring that one down to 0.15. And then you do your production of your C times A, which is your measuring your impact, and then you get your 0.24. And then for the next one, you get your 0.20. Then for that, you do your accumulation of your CA. It becomes 0.24. And then when you do accumulation in the second line, you simply add, and then you move back to your spot to get 0.44. Now going forward, you will have to determine the time of concentration. Now this one here is the time of concentration, but bear in mind here that when you deal with this, there is a procedure that we've shared in one of our previous screens, the procedure for the calculation, whereby it gives you the columns and what is expected in each column in terms of calculation. But now the time of concentration is no longer calculated in the context of the formula, but it's also established through the inlet time plus the time of flow, which is very important. Now, when you speak of the inlet time, you're speaking about that inlet time. And when you speak of the time of flow, you're speaking about the time of flow which for the flow that already is in precedence in the pipe. Now, according to this case, we do not have the time of flow, but we do have the inlet time. Hence, it remains the same as that of the time of concentration. You see, so I believe we all understand that part, and then we are going to move on from that slot until we get to the next. Thank you. Yes, indeed. As well, speaking about the time of concentration, the formula for the time of concentration in this regard is inlet time plus the time of flow. However, when you do the intensity, according to the knowledge that we've acquired from the run of calculation, it came out to us that when we do the intensity, we follow the rules of using the ITF curve. However, in this question, it has been explained fully to us that the ITF curve is represented by that formula, which is equal to 6600 divided by TC plus 45. Now that becomes a constant in this question. However, when you then calculate that, you simply substitute your time of concentration to that formula, and then you get your variables of 134.69. And then you go out to determining the flow. Now the flow that you are determining is calculated in meter cubes per minute. Now the formula to calculate the flow is similar to that we use in the rational method. However, we divide that part by 100 as well as multiply it by 60 in order for us to maintain the units that we are expected to come up with. And note that the AIC is already provided because this is the one, the intercept that we have, the C, which is the coefficient that we had, and the A, which is the area that we had in hectares. Hence the 100, because it has to come down to meters. Now, according to that calculation, we then substitute your intercept as well as one of the variables that we've already acquired as well, which we get 5.39. But now the question comes on to the slope. Now, when you look at the slope, in this type of equation, we have been provided that the velocity of the pipe is 1.8 meters per second, or provided it in meters per second. Now the velocity of the pipe is 1.8 meters per second, and that is the diameter of the pipe, and that becomes the slope. Now the question is, how do we then get that? And the length of the pipe is given as 80 meters, hence I put the L there. That is supposed to be the column sitting there. Now the length is given by 80 meters. Now according to the slope and the diameter, you simply go to the monogram, you read your value of 1.8 and possible the other value that you have of 5.39. Then you draw a straight line with your pencil, and then you read across what other values that you might be getting for the diameter as well as for the slope. Now after determining those, you then go to your design supply diameters. Now in this context, we discovered that we're getting 255, but in terms of the table of the design supply that we have received from the same question, we're getting about 300 as our minimum diameters of a pipe. Then we took that 300, we used it as part of our diameters there, or in millimeters. However, when we discovered the slope, we're sitting at 0.02 in terms of the slope. And then when we go back to the slope of the suppliers, it was 1:80, which represents 0.012. Probably 1.2, I'm not too sure. Let me check quickly. Yeah, looks like 0.012. But now, the same calculation that you might be having, if you look in terms of the slope there, and you look in terms of that slope, that one becomes our minimum acceptable slope in terms of that diameter, and that one is our design, and it's bigger than the minimum. Hence, we adopt our design slope and keep it as it is. And then we go ahead and calculate the time of flow. Now, when we're calculating the time of flow, it transpired as well to us that you simply take the length, you divide it by the velocity, times the 60. That is the length there. And then you simply say 80, you divide by the velocity, which is 1.8 times 60. And then you start getting your variables. Let's say in this case, it might come up as 7 0.74. That becomes your time of flow. And then you determine your capacity by utilizing that as well as that. Because you remember, in order for us to get the capacity, you will then take your area and then multiply by your V. Now in the context, that will be your area and that will be your velocity, so that we can get our expected capacity of 7.6, which is 7.6 there. Now when you move to the next line, remembering that the time of concentration was time of flow plus inlet time. However, in this regard, now we've already acquired the inlet time, the inlet time as well as the time of flow. Hence, we'll be having a different situation in terms of our time of concentration. And then the I again, you go back and substitute based on the variables exactly the way we followed on that one. However, when we get to this context, this is what will be the possible flow that you are designing for. And then as we go forward, following the same procedure of the monogram, as well as the time of flow and all the procedures that we followed in calculating these, is exactly the same thing that will assist us in terms of acquiring from our time of flow our 0.67, and understanding that we're sitting with also 80 as our length and 2 meters per second, as well as 300 and as well as 0.27027. Now, for you guys who are watching this video, you can go ahead and do a practice of the same calculation and try and discover that do you also get the similar variables, and make sure that you do understand how to solve that part of the equation, because that is where probably you'll have to make use of the monogram that have been shared again with your blackboard. Now again, after substituting, we did get the variable for the intensity, and the intensity was sitting at 127.56, and then our flow that we designed for was 5.88. And then there is something that you need to take note of again here, 8.48. You need to take note of these variables here again, because the preceding pipe is 5.38 meter cubes per minute. However, that flow cannot be, you need to compare it to that one, because it needs to be lesser than this one. Because remember, the next flow, the next pipeline that you are designing is sitting at that. Now the question is, it's same pipe, but you must take note that it has got different slopes. That means that one is gentle and that one is steeper. Then that gives you the liberty of saying this one is faster than that one because of velocity and because of the slope. However, you are capturing a very good understanding in terms of the full flowing capacity of your pipe, which is 7.6 cubic meters per minute, and then the flow flowing capacity for the second pipe, which is 8.4. Now, if you look in terms of that, that is indeed it must be bigger than that flow, because it will show that you have a capacity flowing full pipe bigger than that of the flow that is going to flow within your pipe. Similar to the second pipe, that the full flowing capacity is bigger than that of the contributing flow into the pipe. So in terms of the calculation, that is exactly what is expected. Now again, in addition to that, if you look in terms of the slope and the pipeline, that is what you'll be getting. Now, assuming that there is a possibility of cover to pipe, that will be your cover to pipe, and those will be your ground levels, you see. Now, looking at this, in the next questions, they might want you to determine the invert levels at this point. Now, in determining the invert levels at those points, you simply just take the ground level, separate the cover, separate the diameter, and you know the level there. And understanding that you've already calculated the slope of the pipe and you know the distance of the pipe, you simply then separate, when you go down minus the slope multiplied by the distance, and then you get the invert level there, and then you do the same, you get the invert level there. Then you'll be able to understand now the long section, how is it shaping of the same pipeline that is in plan for you in that context. That is it for now, and I believe for our next lessons, we might be taking some further questions based on understanding of people who are watching the video, so that you can get the clarity, you get more clarity with then will action based on your questions. And again, if not so, we will be seeing each other to discuss more about the sewer and sanitation pipeline. Thank you.